Hi, we're looking at exponents today. So what if I wanted to multiply 3 times 3? Times 3 times 3. Okay, is there a better way to write this down? Yes, there is. We can use exponents. Okay, we would write this down as 3 to the 4th power. What we're doing is we're going to have a number up here on top that is called the exponent. And the number here on the bottom, right, so the exponent is resting on top of that, well, we call this the base. That's what the exponent rests on top of. And what does this notation mean? Well, what it means is we're going to take this base and we're going to multiply it by itself some number of times. How many times? Well, the exponent number of times. So in this case, 4 times. That's what we have. 3 times 3 times 3 times 3, right? 4 times total. And you could evaluate the arithmetic here. 3 times 3 is going to be 9. 3 times 3 is 9. 9 times 9, well, that's going to equal then 81. Okay, so 3 to the 4th power is 81. Why would we do this? Why would we try and develop this kind of exponent notation? Well, you could imagine maybe you wanted to get the area of a square. Let's say this square is length 5 and height 5. Let's call them 5 centimeters, okay? How do we find the area now? Well, it's going to be 5 centimeters times 5 centimeters. And what's that going to equal? Well, that's going to equal 5 centimeters squared, right? And we could evaluate that. That'll be then 25 square centimeters. Okay, so we're using this word squared here to represent when something is raised to a power of 2. You could also say 5 to the power of 2. That's also acceptable, but it's very common to say 5 squared because when you raise something to the power of 2, essentially what you're doing is you're finding the area of a square. All right, we can develop this a little bit further. Let's say we take this and now let's try and find the volume of a cube. Okay, so let me draw us a little cube here, something like this. All right, there we go. We've got a cube. So once again, we can say this is going to have some side length of 5, and this would also be a 5, right? So if we wanted to find the volume here, what would that be? Well, it's 5 times 5 times 5. So this kind of repeated multiplication, that's going to equal 5 cubed. Or we could say 5 to the 3rd power, but cubed is often what we will use when we talk about something to the 3rd power. And that'll just be 125, okay? That's how we use exponent notation. And raising something to the power of 2 or 3 has special names. We say 5 to the power of 2 would be 5 squared. 5 to the power of 3 is 5 cubed. When you go above that, you just use the numbers, right? 5 to the 4th power, 5 to the 5th power. No special names there. Okay, what I want to do next is a look at how this notation can be used. Exponent notation here is not too complicated. You have some base, you have some exponent, so you're going to have the base multiplied by itself, and you're going to have n of those bases, right? Not too bad. Let's try putting different numbers in for the base and see what we get. For example, what if we had a fraction for a base? What if we had 1/3 to the 4th power? What does that mean? Well, what that must mean is 1/3 times 1/3 times 1/3 times 1/3, right? What is that going to be? Well, we know how to do fraction multiplication, so 1/3 times 1/3 is 1/9. 1/9 times 1/9, well, that's going to equal 1/81. Okay, so using a fraction as a base is perfectly fine. We can do that. What if we use a negative number as a base? So -3 raised to the 4th power. Well, that's going to be -3 times -3 times -3 times -3. And what does that equal? Well, -3 times -3 is +9. So here we're going to get another +9. So this must equal 81. Okay, so that negative sign disappeared. Why did it disappear? Well, it disappeared because we had an even number here for the exponent. Imagine if we had an odd number. How about negative 3 to the third power? Well, here what we would get then is we'd have 3 of these negative 3's, right? So for this first one, well, this would be positive 9, but now we're multiplying that by a negative 3. So 9 times negative 3, that's going to equal negative 27. So when we have an odd number in the exponent and a negative base, we're going to get a negative number. Negative base with an even exponent will get a positive number. Okay, so that's just sort of how it works out. The negative number flip-flops each time you add sort of another factor of negative 3 here. And finally, what if we didn't have these parentheses? What if we just said negative 3 to the fourth power? What's that going to equal? Well, what this actually indicates is you're going to take the negative of 3 to the fourth power. So 3 times 3 times 3 times 3, right? And so all of this inside here is 81. So what we're going to get then is negative 81 as the final result there. Okay, so that's just a little recap on how we can use this exponent notation and put different types of numbers in as the base. But now I want to focus on the exponent here. So far we've been using numbers like 2, 3, and 4, but what if we had some number like 3 to the 0 power? What does that even mean? Let's see if we can figure that out. A number raised to the 0 power, it's kind of hard to understand what that means. Like, how do you wrap your head around that? See, when we have 7 squared, that's fairly straightforward. We know it's going to be 7 times itself, and there's going to be 2 of these 7s. Okay, no problem. What about 7 to the first power? Well, that's going to be 7 multiplied by itself, but there's only one 7, so that's just going to be 7. That's okay too. It's a little strange, but sure, we could do that. What if we do 7 to the 0 power? What does that even mean? You're going to have, what, 7 multiplied by itself, but there's no 7s at all? So what do we get? Do we get 0 here? Like, what is this? Let's take a look at sort of how exponents behave and see if we can answer that question. Okay, so what if we had 7 squared times 7 to the fourth power, okay? What is this actually going to equal? Well, we could imagine this first part, well, that's 7 times 7, right? That's 7 squared. And now we want to multiply that by 7 to the fourth power. Well, that literally means 7 times 7 times 7 times 7. And now, can we take this and do something with it? We can compact this, right? We see now we're going to have 7 multiplied by itself 6 times. So we can say this is equal to 7 to the 6th power. And this 6 here, we can understand that as 2 plus 4. So we can think of this as 7 to the 2 plus 4 power, and those are the exponents that we started out with. And so what we can develop here is sort of a general rule for how exponents behave. We can say that any two numbers, they have exponents. If you share the same base, then you take their exponents and you add them together, right? That's what this multiplication is actually going to be doing. Okay, so this is a really powerful general rule for how exponents behave. And it would be nice if this rule was consistent when we're using an exponent of 0. So let's try it out. What would we get if we used one of these numbers, one of these exponents was a 0? So let's try 7 to the fourth power times 7 to the 0 power. What do we get? Well, this rule tells us we should get 7 to the 4 plus 0 power. And 4 plus 0, well, that's just going to be 4. Okay, so we're saying that when we multiply these two numbers together, we just get 7 to the fourth power. Now, for that to be true, this 7 to the 0 must be equal to 1, right? Because that's the only way that you can have 7 to the fourth power multiplied by something and keep it as 7 to the fourth power. It must be, this 7 to the 0 must be the multiplicative identity. It must be the number 1, okay? And so that's what we're actually going to get. Any number raised to the 0 power, well, that must be 1, okay? So we're kind of demonstrating this by trying to maintain consistency with this rule. Any number to the 0 power must be 1. 7 to the 0 power is going to be 1. Great. Let's see if we can actually extend this to using negative numbers in the exponent. What's that going to look like? Well, what does this mean? A number raised to a negative exponent, right? If we have 7 raised to the negative 2 power, well, what are we talking about, right? It's 7 multiplied by itself negative 2 times. How can you do that? Okay, so what we want to do is, just like before, we're going to try and be consistent with that rule. So if I had 7 to the 5th power multiplied by 7 to the negative 2 power, what would I get? Well, to maintain consistency, I should get 7 to the 5 plus negative 2 power. That's the same as 5 minus 2, okay? And what's that going to be? Well, 5 minus 2 is 3. Okay, we should get 7 cubed. Let's write this down, expand it out, see what's actually happening here. So 7 to the 5th power, that's going to be the same as 7 multiplied by itself, and we're going to have 5 of these 7s. And we're going to multiply by something here, right? And that's going to equal 7 multiplied by itself, and we'll have 3 of those, right? So what are we going to actually multiply right here in order to get 3 of these 7s? Well, if we look at it, what we have to do is we have to cancel out these 2 7s here, right? If we can get rid of those 2 7s, then we'll be left with 7 cubed. So to cancel that out, we're going to multiply by 1 over 7 times 7. That's what's going to do it, right? If we do that, these 7s cancel out, and we're left with 7 cubed. So 1 over 7 squared must equal 7 to the negative 2 power. That's what we are discovering here. 7 to the negative 2 is the same as 1 over 7 squared. So we get another way of understanding negative exponents here with this kind of general expression where any number, any base raised to a negative exponent is the same as 1 over that base raised to the positive version of that exponent. Okay, so there we go. That's how we can understand negative exponents. Let's see if we can try some practice. We're starting out here with 3/7 to the 0 power. Seems a little tricky at first, but remember that any base raised to the 0 power is just going to be 1. Okay, so that's actually pretty easy. Here we have 5 raised to the negative 1 power. We saw that's the same as 1 over 5 to the 1 power, which is just 1 over 5, okay? And so we use this negative 1 exponent to represent taking the reciprocal of something, right? So taking the reciprocal of 5 would just be flipping that over to get us 1/5. Here we've got negative 3 squared, so that's the same as negative 3 times negative 3, and that will just give us a positive 9. Okay, not too bad there. And finally, this negative 2 to the negative 4 power, that's the same as negative 1 over 2 to the 4th power. And what is 2 to the 4th power? Well, that's going to be the same here as negative 1 over 16. Okay, so there we go. That's how we can look at exponents, and we can use any integer as an exponent, and we understand what that means. Now, you might imagine expanding this. What if we did more than just integers? What if we looked at rational numbers as an exponent, right? So you could have fractions in there. What does that do? That's an interesting question, and that is going to be a lesson for another day.